the objective for this chapter, for chapter 14, is all about light. Okay, so today we're going to talk about just the properties of light. This is not very mathematical based. A lot of conceptual stuff is involved here again. Okay, so we're going to look at four things. First, we're going to identify components of the EM spectrum. EM, I'll put it for the first time.
Erica Maffa?
Electromagnetic, yes, Erica Maffa, thank you. So we're going to call it EM though from this point on, but it means electromagnetic, okay, not Erica Maffa.
Wait, isn't that like little light turns like rainbows and stuff?
Yeah, it's part of that, yep. The visible spectrum is part of it.
Did that in chemistry?
So, we're going to recognize the fact that light has a finite speed, and we'll talk about that. Describe the brightness of a light source and how it's affected by the distance, and then calculate the frequency or wavelength for all or any EM waves. Okay, let's first slide here. Okay, I'm going to explain what this is. You do not need to draw the image. Just write down the definition for now, please. So first, electromagnetic wave is what we're defining. An electromagnetic wave is the following. A transverse wave that consists of oscillating electric and magnetic fields. Hence the name electromagnetic, two parts. And those fields are at right angles to one another. Okay? We'll talk more about fields and force fields and electric fields and magnetic fields and what they are. Okay, force fields are a real thing. It's not like Star Wars, a force field or the Force kind of thing.
Oh, that's what Dash Incredible has.
Okay.
You. He's like, no force field.
So what you're seeing here is the following.
Wait, I have a question. Force fields, don't they put like... Oh, never mind.
Wait.
Yeah, but force fields are more like gravitational force fields and magnetic force fields. Not like this imaginary thing that's not there, you can't see
You
it.
think of like a force field as like an electric fence?
I mean, mentally sure, but that's not what they are really.
Oh, so
A
it's
force
not,
field is like the field of gravity that we are currently in. We're in a force field right now.
so it's not like at like a museum that like something has like a
No.
field around it? Or is that like not even a real thing? Is that just from movies or is that...
Yeah, it's really just
I
for
don't really
movies.
hang out at like museums. So
Yeah, I don't know how. So, here's what we're noticing, and watch, I'm going to draw on here. You do not have to draw this, but watch how I draw over it. The magnetic field is this one, and I'm going to highlight it. You see the blue line appearing or no? See the blue line appearing right here? Okay. That's the magnetic field that's produced. Now, the electric field is in gold here. I'll highlight that in orange.
These colors are really spot on with the dotted lines.
Okay. So,
you're a good tracer.
the electric field is also transverse. Notice these waves are transverse because their motion is vertical of the wave particles, but the wave itself, look at the direction of the wave itself, is following this red line down the page. So they are perpendicular still. Now the key is this. They're perpendicular to one another. And I'm going to show you that with my hands on the board because it's tough to see. If this is the electric field right here, okay, this is coming out of the board like this right now. That's what's happening right now. That's coming out of the board at a right angle. So there's a right angle every time. And then suddenly this one is going into the board, and this is going down. So this is like down and into the board. Okay, that's the second wave. It's still at a right angle though.
Oh, so they're changing.
Okay.
Wait, but why do they change it?
Then-
Why don't they go just
Because
straight
they're oscillatory waves, and we talked about periodic waves and oscillatory waves as having a trough and a crest. Okay. Next, in the third part, we have again at the top, we have this electric field at the top, that's this, and the magnetic field is coming out of the board again right here, that's this blue one. Okay, so it's,
They're overlapping.
yeah, they're coinciding more than anything.
Wait, is that thing that they're gonna become like, that they're gonna add to each other?
No superposition here, no. Because they're at different angles.
This is like
But-
when flip
No, the
when
two
you
at
like
the bottom.
Erica?
Wait, I'm sorry.
when you like let something go or like you pull it apart and then it goes back and I don't know if this like if you know what I'm talking about, but it like looks like it's like going like that, but it's really just spinning. You know what I'm saying?
I think,
It's like you have seen in Chinatown, like they have those things all the time. That's exactly what it is.
I mean, it looks like a double helix.
I thought you know what I was talking
Sorry.
Don't go fat chew. Don't go fat chew.
Come on.
Wait, that thing that's like that video I missed, like that video from when I was gone,
Uh-huh.
it had Like, say one of them was 3 and one of them was 5 and they became 8.
That was superposition,
So that
yes.
does not happen.
Not this, no.
But if they were going in the same, if they had the same angle, that would happen.
It could happen, sure. Yes, it could happen.
Like
Same
they
angle.
collided.
But these are perpendicular to each other, so it wouldn't happen.
Wait, these are completely perpendicular, these two?
Yeah?
They don't look perpendicular.
Because you have to visualize how...
No, I'm talking about like these two. I'm not talking about these other ones. Hell, totally were missed.
They are perpendicular. This is going up and down. This is going left to right. In the board, out of the board. Out of the board, in the board.
Yeah, but I'm
Up,
talking about
down,
this to
up,
this.
down. They're not.
These two, those two are, but not those two.
They have like
No, they're not.
They have no relation. The
No.
yellow and the.
No.
Oh, okay, I'm sorry.
It's all right. So,
I'm just trying to.
the next we're going to look at is the electromagnetic spectrum itself. There's a lot to this. You do not need to write all this. Okay, we're going to talk about this. Okay, and I'll tell you what you should know. First, Erica, just sing it once and then don't ever sing it again. Go. Because you've sung it like 30 times the last few days.
Get out. Radiation, visible light.
She's practicing
Ultraviolet, X-rays, gamma rays.
Good job. So, Erica just sang down the line here. Okay. She's saying from the radio waves down to gamma rays. Thank you, Erica.
Don't be too fast, guys. If you want to learn the song, I'll teach it to you.
You're babe.
Now,
I'm a babe.
here's some things we have to point out. First,
You look like Prince.
the first thing to notice. Radio waves. Radio waves. The wavelength for radio waves is bigger than 30 centimeters. Okay? Everything after that is going down in wavelength. Look at the next one. Microwaves are between 30 centimeters and a millimeter. Then infrared rays are between a millimeter and 700 nanometers, which is even smaller. And they're getting smaller and smaller and smaller until you get down to gamma rays, which are on the order of 10 to the negative 5 nanometers. So we're talking about things on the order of like picometers, very, very small. So you're noticing that lambda max... Stop talking, Helen. Lambda max occurs at the top here. And lambda min occurs at the bottom of the electromagnetic spectrum. So our radio waves are the biggest waves that exist in the electromagnetic spectrum, and the smallest are gamma rays. And now what you'll notice as well is that the inverse relationship exists for frequency. Look at the bottom of the chart here. The frequency are in the order of 3 times 10 to the 22nd hertz. Whereas here, they're on the order of 1 times 10 to the 9 hertz. So this is an omega min. And this is an omega max. Okay, so again, we see that relationship. The relationship here, that the bigger wavelengths have the smaller frequencies. And the smaller wavelengths have the bigger frequencies. You're seeing that they're opposites. So as the wavelength increases, the frequency decreases. Again, where does that come from? It comes from this equation from last chapter. And we're going to talk more about this today. Velocity, or the speed of the wave, is equal to the product of the frequency and the wavelength. Now, electromagnetic spectrum waves all travel at the speed of light. So this V here that you're seeing is a constant. So if V is a constant, okay, V is not going to change, it's a constant, it's the speed of light we'll talk about in the next slide, that means that omega and lambda are going to be inversely related. So if omega goes up, so if the amplitude goes from the the frequency goes from the min to the max, the wavelength, lambda, has to go down. So lambda is going to go from its max to its min. So what you want to make sure you notice is that there's an inverse relationship here. The frequency and the wavelength are inversely related. Okay? We talked about the period and the frequency being inversely. The same thing applies to wavelength and frequency.
So is W wavelength
Okay.
and period are
Similar.
similar? Yeah.
Similar, yes. Yes. The period is the time it takes for one wave. The wavelength is the distance traveled by one wave. Okay? It's like X and D. They are related, very much so.
What is, like, I know we always talk about wavelength, but, like, what is actually the difference? Is it, like, the smaller the wavelength, or, like, I guess the smaller,
Smaller
than, like, the more detailed it becomes?
Not more detailed, just higher frequency. It just means that the wave is oscillating faster in a sense. It's going through its troughs and crests quicker.
You kind of explain that. What does that even mean?
Like certain wavelengths can be picked up by certain receivers. For example, an FM transmitter, AM transmitter, they receive different lengths. So, for example, if you want to transmit a signal to your car, you tune into 99 point whatever megahertz. Okay, you turn it to whatever station it is, right? The length of the wave itself is, in a sense, a property of the wave that allows it to be either interpreted, received, or transmitted through different boundaries.
Well, so if it was a smaller wave,
it would have a different effect, exactly. So these small waves that are gamma rays, these can really have an effect on your body, and they can actually be used to treat cancer because they're such small waves that they can get into the cells and actually affect the cancerous cells. That's when people get cancer treatments, when they put X-rays or gamma rays to help somebody that has cancer. They're actually pinpointing the cells that have the cancer, and they're sending waves in them to try and kill the cancerous cells. Because they're on such small levels of,
That's what
I
chemo
thought
did.
they all kill every cell.
Some of them get killed that they don't want to, but they're trying to target the ones that are specifically cancerous.
So why doesn't it work when someone...
Because it's on an order that's so small that we haven't really, I guess, understood yet. I don't know the exact answer. I'm not a cancer scientist. I can't lie to you.
Isn't it all
Okay.
Isn't it all really bad?
But it's better than dying from cancer.
So bad for you, so are they all really?
I don't know. I don't know too much. I'm not going to get into this right
Wait,
now.
I watched a horror movie and they put someone's head in a microwave and then their head blew off. Would that actually happen?
Probably. A microwave would do that to somebody, yes.
So against
All right, now, what we want to talk about are applications of these waves. First, radio waves. Simply, AM, FM radio, and TV. Now, obviously, TV is not on waves anymore. TV comes in your fiber optic cables. Okay? But TVs used to have antennas on the back of them, and those antennas used to receive the different waves. Second, microwaves. The obvious, answer, a microwave itself, which, by the way, a microwave, what it does is it extracts the moisture from the actual food element to heat it up. And that's why, if you've ever heard the saying, when you heat up like a slice of pizza, put a cup of water in there with it on the side, and you won't get that spongy crust to it. Okay? Did you know that?
When we do rice, we
Put-
put in water in the rice.
With rice, if you're ever warming up rice, you take a little bit of water, put it all over the tops of the surface of the rice, and it won't get the rice to get all dried out. Okay? Because the microwave extracts moisture out of the object. Put a cup of water in with a slice of pizza, I would use a toaster oven for a slice of pizza. But if you use a microwave and you're in a rush, because it comes out much better. If you use a microwave, put it in for a minute, but put a glass of water next to it, and the crust won't get all spongy. Okay? I read this stuff online. Check.
Stumble upon?
So how you put French fries in the microwave, they get moist though.
They get soggy.
Yeah.
What?
They get all what?
They get moist and soggy.
Well, because it's drawing the moisture out, and that the outside of a French fry is that crisp outside, But once it's been refrigerated, it just becomes like a potato in a sense. So it's like you're heating up mashed potatoes. So it's going to become mushy.
Because I've always tried to do that.
Yeah, it's because you're not if you put it in a toaster oven though,
You're really not for that.
Put
Alright,
it-
toaster oven's better
wrap
for
it in-
too. Microwaves aren't
Yeah,
good.
microwaves are really bad.
well, the radiation from it, if you stand next to it a lot, can hurt you. But that's you need to be a person that stands next to it every time and waits,
I hate
you should really walk away from the microwave when you turn it on.
You have a toast oven?
I do have a toaster oven.
Great.
Wrap some fries in tin foil and put them in a toaster oven. It comes out much better.
No, because if the tinfoil gets caught on...
They're amazing. Toaster ovens are great. Yeah.
Oh, if you put Totino's pizza rolls in the toaster oven, it's life changing.
It's so good.
You've used what did you use in the past? The microwave?
I always the oven, the real oven.
Oh yeah, toaster oven's great.
The toaster oven.
Oh, it's much better.
Have you ever tried Pompeii?
I hate the microwave.
All right, let's keep going. Now,
So good.
next, microwaves.
You need them to be like
Helen, that was
okay.
a curse word.
Microwaves next. What was a curse word?
Helen.
Helen. Microwaves next involve radar as well. Okay, it's a big component of it. So radar that's used to track, for example, say missiles or ships in the air, or underwater like sonar. Okay, you're using sound waves, a little different, but the idea of using radar in a sense. Okay. Next, infrared. Let's discuss this term. Okay, there's a lot to talk about with infrared, and we don't have much time, so you need to listen, not talk. Infrared here, we're going to be talking about waves that occur that represent thermal imagery, so heat imagery. So for example, if somebody is standing behind this door and you had an infrared camera, with a normal camera you could see their body over here, but the door would block their view. But with an infrared camera, you would see their heat signature behind the door. So when you see people in the military, when they wear the goggles, they go in. So when they captured Osama bin Laden, the dogs that were used in that, actually the canines, they were equipped with infrared goggles that worked on dogs. It was amazing. So they were the ones that led the attack that could see through all the walls. Then they all had the infrared goggles on so they could see all the people that were there. In addition to that, that was an amazing, by the way, an amazing heist.
Zero Dark 30.
No, not Zero Dark 30. It has not been recreated, really, this one. But it was when they captured Osama bin Laden, and they also used a helicopter that was actually no sound at all. There was no sound from the choppers. It muted the sound. It was absolutely crazy.
How does that happen?
How is that possible?
There's a lot that goes into it. I'm not going to talk about it now.
Explain it to me and I
But the
didn't
thing was
understand.
in the movie.
Read, go online and Google it, please. There's like thousands of articles that describe all about how it worked. I've read a bunch of them. And we could talk about it another day.
But it's still like a helicopter,
Oh.
Yeah, but we'll talk about it another day. So, infrared. Infrared is the idea of things. Guys, I'm shunning all of you right now because we need to keep going. And I said that twice already. So I can't stop today. We have 10 minutes or 15 minutes left. Infrared waves. Okay, infrared waves are things that occur below the red part of the visible spectrum. So if you draw out the visible spectrum, you see the following. Okay, red, orange, yellow, green, blue, indigo, violet. And notice you have red at one end, and right below the red spectrum or the visible spectrum is infrared. And you have violet on this end. And right above that you have ultraviolet. So these names are not coincidences that they have the word red in them and violet in them. Infrared, infra means below, red meaning below the red. So for example, you're seeing here is that the frequency of infrared, the frequency here of infrared is below the frequency of the visible spectrum. The frequency of violet is above the violet or the end of the visible spectrum. You see that the numbers get larger. So ultraviolet means frequencies above violet. Infrared means frequencies below red. Okay, that's where the titles come in. Infrared is good to know for photography and for heat signatures. That's where it really comes into play. Okay, molecular vibration spectra simply means how fast the molecules are vibrating, which is a measurement of its heat anyway. Okay, it's a measurement of heat, the molecules vibrating. For ultraviolet, we're looking at sterilization of instruments that are medically used. For example, believe it or not, people use now these little cases for their toothbrushes. And they put them in there and they, get rid of all the germs on a toothbrush using ultraviolet rays. Okay? Personally, I think that's a bit of a germaphobe, but, everybody's different.
Are you serious?
Okay.
That's how people get sick.
From their own toothbrush? No.
Yeah, no.
Maybe from sharing a toothbrush.
I'm supposed to use the toothbrush more than like 3 months. I feel like
Guys, if you use
2 months, you're not allowed to use one.
If you use your toothbrush and clean it with hot enough water, it will kill all the germs its own. Okay? It will. It will. Don't become a germaphobe. People that become germaphobes get sicker than anyone else. Because it is true. There's a lot of articles. I can put them on news form if you'd like me to. Okay, a lot of people that are germaphobes actually get more sick than others. Because they're so afraid of germs that they kill all the germs in the world. And then what happens is the stronger germs end up surviving. That's like germs in the hospital. People that are always about all this stuff, I never use any of this. I've only been sick literally once in the last 4 years. And it was 2 weeks ago when I had that minor flu. Okay? But stuff like this is only good to some extent. If you sneeze on your hand and you're sick and you have nothing else to clean your hand with, then definitely use this. But people that walk in the room every time and use this stuff, it's actually killing off all the germs that want to be on your hand. The good germs. Okay? There are such things as good bacteria. When you're a kid and you roll around in the dirt and you eat worms and stuff when you're a kid, those are all good things.
I'm trying to justify
your kids should eat dirt, and they stuff like that happens. People that are afraid of that, they're gonna end up being just germaphobes the rest of their life and getting sick.
Movie with Jake Gyllenhaal when he's in the bubble?
Bubble Boy?
I love that movie.
Yeah, Bubble Boy. Thomas.
So you know how waves eventually dissipate?
Yep.
And they spread out? So does that mean the ultraviolet goggles and stuff, you might see behind this door, but if it was 10 feet farther, you wouldn't be able to see as well, or?
The infrared, you mean?
Sorry.
That has to do, though, yes, because when it goes through a wall, it's going to change the wave. So once it goes through some sort of a medium, like a wall or concrete, it's going to affect it for sure. they're not going to go on forever, so it would change it. The cameras are good enough so they can compensate for that density that's there and still show a correct image. But beyond maybe one wall, it won't be able to see. Okay? Helen?
Does the size of the wave, like I guess the wavelength, does that affect how far it can travel?
Not how far, but what medium it can travel through.
Okay, so the infrared waves can travel through a wall, but then what?
But then you're not going to use infrared waves on looking at like the heat signature in a cell of an organism because the size of the infrared waves are bigger than the cells themselves. Okay?
Okay, but then like, what about like X-rays you use on like a body, and you can see.
It has to do with looking at the bone density. I'm going to get to that. Let me talk about X-rays. So X-rays. We're looking mainly, and you guys have heard of this before, obviously, with bones and teeth. Okay? And what it does is the X-ray is able to determine the density there. So when there's a break in your bone, it notices that there's no density existing there, and that's what you're seeing in the picture. So when you who's broken a bone before? Okay, have you seen? You broke what?
I broke Kara's arm by accident.
Have you seen the X-ray for it or no? Have you seen an X-ray of a broken bone? You can see the actual, like the snap in the bone. And what you're seeing is the fact that there's this dense bone, and then there's like this gap because there's a break now suddenly, and then there's this dense bone. If you've ever had like a partial fracture where the bone cracks a little bit but it doesn't break through, you'll see this little propagated crack. And that crack is like the existence of that crack is the existence of a space between the bone where the space shouldn't exist. That's that little line you're seeing there. Okay, that's what that crack is. So it's really looking at your density of your bones.
My friend broke her femur, and she had to get like pins in her leg. And I saw they like showed her X-ray.
You can see the pins, right?
It was so gross.
Yeah, you can see the actual pins also because the pins are metal, or they might have been plastic. I don't know. It depends on what they were. They were metal? Okay. And they do come up under different densities. And then finally, gamma rays. Okay, gamma rays. Gamma rays are really, really important, and they're used a lot in structural engineering. So if you want to know if there's some sort of structural flaw with the foundation of this building, and you want to see like, is there a problem or can there be an issue down the road, and you want to look for different cracks in the structure, you can't use certain waves. But gamma waves actually, or gamma waves, or rays, doesn't matter whichever term.
Rays.
I put them together, yes, I know. Can be used to find those structural locations of lack of integrity, okay, or where there might be a flaw in the actual beam. So if there's a crack in the I-beam that's holding up part of the building, that can be used to find that. Other ones or other ways you've seen gamma rays, okay, food irradiation. It just means if food has some sort of radiation involved to it, or it was made with some process that might have radiated the cells or given them some radiation, you can irradiate it using gamma rays. And that's done not by us, but by food specialists.
So, in the Hills of Eyes, what kind of radiation?
I have no idea what the Hills of Eyes is.
Oh, it's such a good movie.
This is a scary movie.
Never heard of it. What? That's probably gamma rays and nuclear waves in general. There's beta, alpha, and gamma. One of the three.
They got eyes like up here.
All right, let's go, guys. Come on. Next.
I'm done. Yeah.
Next definition is speed of light. First, the speed of light is a universal constant. Okay? It is a constant. It has a finite value. Okay? Yes, similar to that. The speed of light is simply the maximum speed at which anything can travel in the universe. Again, nothing can travel beyond the speed of light. And that's the idea of why time travel is impossible. Okay? Because nothing can break the speed of light boundary. So what we're seeing here, okay, is the speed at which all EM particles move in a vacuum. That's the key. In a vacuum. What does a vacuum mean? Well, a vacuum is the absence of a medium. So outer space is a vacuum. There is no medium. There are no molecules there to interact with the light waves. That's why in space you can't hear someone yell. We always say, if you scream in space, it's like no one would hear you screaming in space because there is no medium. And space requires a medium. It requires molecules to vibrate to make sound propagate. But light itself can travel through a vacuum or a space where there is no medium, which is why it's so incredible to think about because it comes all the way from the sun. Okay, and this is the speed it's traveling at approximately. It's really 2.99. There's a bunch of other decimals afterward. We're approximating it. Okay, one second. One thing to note, okay, and this is an interesting fun fact I always think people should know. You only see light 8 minutes after it is produced by the sun. It takes the sun 8 minutes for its rays to reach the earth, actually. So if the sun ever exploded, what would happen? We wouldn't notice it. You would have 8 minutes really left, okay, until the sun went dark or until the sky went dark. So if one day the sun just disappeared and we lost the sun, you could say, "Oh my God, it exploded 8 minutes ago." About, okay, because it really does take 8 minutes, and it's kind of crazy to think about because look at the speed of light. It's 300 million meters per second. What's a meter's this big? Imagine traveling 300 million of those in a second. The speed of light is so incredibly large to think about how far the sun really is from us. Okay? Which is why we'll never really send somebody to the sun, because they're never going to make it there before they die. You would have to send like a family of people that would keep reproducing over time and have generations and generations to ever get to like something like the sun.
They sent him a little like a robot to Pluto, and it came back.
Again, to Pluto. To Pluto for sure. Pluto is not. Is Pluto?
It's not a planet.
I know, but I'm trying to think if it's further or closer than the sun is.
It's further. It's so far, and it took.
The solar system is not drawn to scale, so don't assume because you've seen these diagrams that you think it's further.
Well, I mean, I did my own diagram.
Solar system is not drawn to scale when you were a kid. I forget which is further away, the sun or Pluto. The sun actually might be further.
Pluto, it goes Jupiter. Saturn,
I understand, but the Earth is here, the sun is here, Pluto is here. You don't really know where it is.
The sun, Mercury, Venus, Earth.
Yeah, but they're not all.
Yeah, but we don't know if it's proportional. You don't know.
I'm 150% sure that the sun is closer than.
Okay, look it up. Chaz.
It was so old I fell off my desk.
I mean, the Earth would not survive without sun.
Oh, so we couldn't.
Yeah, you would go going back into the ice ages for sure. Yeah. Yep. But the sun's not exploding anytime soon, so don't worry. We're good. We're good. It's got a lot of life. We can estimate how much life is left, and there's a lot of life left.
That's
all right.
Scary, though.
Yeah.
So again, I know it is kind of scary. This speed here that we're looking at is the maximum speed. Okay.
Hand up.
Let's take a look at an example.
Can you go near my pencil, please? What? Someone spilled water and they got all over the thing. Thank you, bro.
So, FM radio, its band extends from 87.5 to 108, and you've noticed this obviously. Okay, 87 band is like the actual, like the band of waves. Okay? Now, notice the units are not hertz, but they are megahertz. And you've seen MHz next to your radio station sometimes. It says MHz for megahertz.
Like megahertz.
Okay? What? Yes, like megahertz, exactly. I don't know what that was saying. What are the longest and shortest wavelengths in this frequency range? Okay? Longest and shortest wavelengths in this frequency range. So, for this kind of a problem, let's discuss. First, EM waves all travel at the speed of light. So we can start with this formula here. Let's all start with this, please. Okay, but rewrite it instead of velocity, write C equals omega lambda now. This is going to be, let's write C equals omega lambda. You need to write this down. This is not going to be given to you as a formula. This is given on the left. This was on your last test. This will always be given to you. But if you know it's an EM wave, you replace V with C, and C has a value. That will be given to you. Okay? So the velocity in this case is the value 3 times 10 to the 8 because it's the speed of light, because it's an EM wave. Radio waves are types of EM waves.
It's not easy it's not hard to remember, but are you going to give us the value of C?
I am. It's going to be at the bottom of this, with the little g and with big G down there, with the other two constants. Little c will be down there as well.
So C is only going to equal frequency or omega times lambda when
It's an EM wave.
That's the only time.
Yep.
Okay.
Okay, again, this holds true, as Erica just said, when it's an EM wave. When it's any other type of wave, you need to know what the velocity of the wave is. Like the velocity of sound is 343. Okay, it's much less. This is 300 million. This is 343 for sound. Okay. Okay, so any other wave, use this. But for EM waves, use this. Now, notice, what did I say a little while ago? C is constant. So we're looking at two different frequencies, omegas. So as omega goes up, lambda goes down. Remember that. These are inversely related. So let's list our givens, please. Omega min, the minimum value of omega in this band wave is 87.5 times 10 to the 6 hertz. Why did I put 10 to the 6?
Because that's what mega is.
Very good, Helen. That is mega.
Go Helen.
And then for the omega max, it's 108 times 10 to the 6. Okay? Those are the two values that we're going to use for omega to find the corresponding lambda values. What was the speed of light again?
3 times 10 to the 8.
Yeah, 3 times 10 to the 8 meters per second. So take a look. We have two problems here, really. The first problem, we're going to use C and we're going to use omega min. The second problem, we're going to use C and omega max. Okay? But remember that when you use omega min, the answer you get is going to be lambda max. But when you use omega max, the answer you get is going to be lambda min. Because they're inversely related.
Oh, that's
Okay? They're inversely. So in your formula, here's what your formulas are going to look like. Ready? Let's break it into two parts. First, with the 87 on the left-hand side, you're going to have C equals omega min times lambda max. And here you're going to have C equals omega max times lambda min. So again, what are we trying to find? We're trying to find the wavelength for each of these scenarios. But remember that when you minimize the omega, you're going to maximize the lambda because they're inversely related to each other. So at this point, what you can do is you can plug in. Solve for lambda in both of these cases. Okay, you're going to get C over omega min equals lambda max. And C over omega max equals lambda min. And then you can plug in. And what you'll notice is this makes sense. Look at it logically. You're taking some constant C and dividing it by a small value, omega min. That'll give you the bigger value, lambda max. But then when you divide C by a big value of omega, you're going to get a smaller value of lambda. It's like taking a pizza up and instead of dividing it into 2, now you're dividing it into 8. Everybody gets a smaller piece, right?
Oh, but
because you're dividing by a bigger number.
Oh.
Okay? So at this point, you're going to plug in your values. You have 3 times 10 to the 8 over
87.5 times 10 to the 6. That's 3.43 times 10 to the 12.
It is most definitely not. So be careful with your calculations, calculator. Be careful. 30 seconds, 30 seconds. Now we have 108 times 10 to the 6 over here, and that'll give you lambda min. I encourage you, I'm going to put the keystroke down, but you must practice this. You must practice this. In your calculator, here's how you're going to enter it. You're going to type in 3, then you're going to press second, and then there's a little comma, and above the comma it says EE in yellow, and it'll appear like this in your calculator. Then press 8. You don't need parentheses if you use scientific notation. Okay? If you do it the way I'm telling you, you don't need them. Over 87.5 E6. Okay? That will give you an answer of 3.43 meters. Over here, your answer will be 2.78 meters. If you have homework, it's on Moodle. You should read about it tonight. Just read through it. Okay? If you want to see how you did as your grade, just hang out.